Yeah. So, you guys, today what I want to do next is I just want to kind of finish out this number thing, which is helping you to know how numbers originate in the lab and then how you handle them as you start to put them into calculations and conversions. Okay, because a lot of people miss this little slight piece and they hear about significant figures. Who all heard of those? Sig fig and significant figures, and it's like, but they don't actually know where that came from. They just do the rules and they just do it, but they don't actually know where it originates as a lab practitioner. So the way to kind of explain this is there's two pieces. One is accuracy. You need to understand what accurate means is like how close the measure is to a known measure. So if I want to know how accurate the scale is, I literally have to get a known mass that's certified and clean. I handle it with, literally I put on cotton gloves, and I put my oily hands on it, and I set that thing on the scale, and it shows me that, oh, this thing is fairly accurate, right? But if it showed this, that I could still do a measurement of what, it's supposed to be 20, but it comes out 19.95. So how accurate is accurate? So one of the measurements we do would look like this. I'm not going to hold you to this, but the way it would work is I do the 20 minus the 19.95, I get 0.05. So that is an idea of how far I'm off, correct? But how far I'm off matters by how big I measure. So I then divide it back up by the 20. And that gives me a percent. So case in point. So if I'm doing a measurement of length, and I'm measuring 100 centimeters and it's off by plus or minus a centimeter, right? The tool I give you, you measure it's a 101, you measure it's 99, you measure it's 90, right? Or 100. Then we're going, oh, it's off by 1 centimeter, but I've only measured 100 centimeters. So that's 1% error. I just do the 1, that amount I'm off divided by the 100. If I had been off by 1 centimeter and I measured from here to the moon, now I'm a millionth of a fraction of a percent off. Very accurate. But if I measured, the size of that opening and I was off by a centimeter, now I'm 20 to 30% off. I'm way off. So the error relative to the size is calculated by doing this. And that's called percent error. But for you right now, all I want you to know is the understanding of accuracy means there's a standard mark somewhere, and we're trying to figure out how close we are to the standard mark. So if I pull up a centimeter stick and I say it's a centimeter long, you're like, well, relative to what mark? If you nerd out on it, the mark is held actually close in Boulder, Colorado at NIST, right? We actually have the the United States National Standard Lab sits in Boulder. So if you go in there, they have everything from, like if you're nerdy and you want to know that your time is right, they have the atomic clock that sets time for the whole country. They have the 1 meter bar that represents 1 meter. They have the measurement that they do, and I'm just making this up, but they might do it some other physics way to get it exactly right. But they hold the standards. But from that, what I did, like when I was in industry and stuff, sometimes you had to have standards. When I worked as a radiochemist, which doesn't mean I did chemistry and listened to the radio, but I test for radionuclides that were in the water, like from Rocky Flats. Okay? We had instruments that tested radioactivity, so they would send out standards. They were marked. I had an ID on them, but I didn't know what they were, and some of them was blank, and some of them had a certain amount, and I just ran the samples all the same, and I said, here's what I think this is, and then they could verify how good our techniques work, right? That's accuracy. How close to the known amount? Easy enough? Okay. Precision, which kind of gets interchanged with the word uncertainty. So the technical terms are slightly different, but here we'll just kind of mix and match it. And that's common. That's what most scientists do. They could say precision, they could mean uncertainty and vice versa, but we're not going to get into that so much. Precision measures how close a tool or operator is to being able to replicate their work. Okay? So that is more along the lines of, when you're picking out 0.1, like you were saying, it's 274.1, right? That gives a little more precision than somebody measuring 274. Okay? And so by saying 0.1, you're trying to say you're more precise, right? You can be off in the tenths. When someone says 274, they could be off in the ones, right? 74, 75, 76, right? But somebody might actually say, well, I'm not that good. I'm actually 270, plus or minus 10. That's precision. Okay? It's how good the tool is. It literally is. So when we go to measure that with our tools in the lab, we take that standard measure and put it on more than one time and see how consistent it pops up that number. And then I have a measure that tells me that. It could be me, the operator, or if I'm doing a process, like I'm making a chemical, and I get through and I go, oh, I started with this, I should have made 80 grams, but I only made 75 grams. That's kind of my percent yield, right? If I do that process over and over and over again, then I'll get a number of precision, how good I am at replicating that procedure. Now, how that matters to you guys is when you pick up an instrument in the lab, you need to understand precision. Accuracy is probably done for you. All right. So you'll have, say, like a gas. You guys are you're in the dental stuff today, right? So you might apply gases, right? Yes, no? You might put somebody on the mat and then turn on a flow. Mm-hmm. Correct? All right. So that flow meter is important, right? We're talking laughing gas, for example. Yeah. I mean, if that flow meter is screwed up and they're getting way too much nitrous in there, it's not going to go well for them. So somewhere you had to do, there's accuracy associated with that, which means to you guys, there's probably a technician that comes in once a year, verifies the flow, and stamps that and says, this reading is good, like accurate. Mm-hmm. That makes sense? Okay, now, beyond that, there's the precision of what you read off the gauge. So you say, okay, I'm flowing 5 mils a minute. Well, maybe that's good enough for what you're doing, but maybe what you have to tweak is 5.3 mils per minute, because the 0.3 makes all the difference in the world. You set it at 0.2, you set it at 0.1, it's going to be a lot different. That's precision. Okay? Now, to be perfectly honest, the instrument accuracy, what we call having a better instrument is actually called uncertainty. It's the measure of uncertainty in the instrument, but we usually just call it precision for in here. It's okay. So, on here, I would do it over and over and over and over again. I'm measuring 20 every time and see how it's varying in what place. Where's it really varying? Okay, these are tenths and these are hundredths. So its uncertainty or precision lies in the hundredths place. This tool is good for the hundredths. Follow? Now, in science, we pick up a scale, we can communicate how precise it is by how we write the number, just a single number. We don't have to do this exercise and then say, oh, it's 20 plus or minus 0.05, which is true here, right? Follow? And so what we do in science is the last digit we write is the uncertain digit. That's the key. That's the secret sauce. Like I want to communicate to you. When I pick up a tool, the last digit I write is the uncertain digit. So on this, I wouldn't write, even if I nailed it, like this came out, I wouldn't write down 20. Because by writing 20, I'm communicating to somebody that I'm uncertain here. And that's not true at all. I don't want to write this. Because that means it's a little better in here, but not as good as it's supposed to be. I'm going to write this because of what I know about the instrument, which is right here. All I have to do is make sure that the last digit I communicate is where the uncertainty lies. Just to compare, you follow the idea? Let's say you did that. Now you go in, you get an experiment. The tool looks just like this. You're getting the 20, you're putting it on every time, right? Now here's your numbers. Yours come out like this. 21.00, 22.05, 19.065, 18. Right? Where are you really varying? Way out here? 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 Really? 18 plus 2, I'm at 20. Right? You're varying here. You see it? 21, 22, 19, 18, the plus or minus is somewhere in the ones. You see it? So what you write down, well, I measured 21, but that's all I can write, because here's where I'm uncertain. This tool does this. 19. Yeah. Yeah, why would it be that? Why didn't I write that? And this is what I'm telling you. In science, because we know this is uncertain, these are the same number. Not mathematically, but they are the same number off the instrument. They measured the same thing. Because it's this big with this much uncertainty. So I automatically get used to thinking it when I see it. Oh, that's not 21, that's 21 plus or minus 2. Now when I see this, I go, oh, it's 20 plus or minus 0.02, something like that. I'm making up the last digit, like 0.02, maybe it's 0.05, but you have the right idea if you understand that's where it varies. And that's, you actually made your own point. You could have written 19 and she could have written 21 and you are using the same tool. It's not very good. It's off in the ones.
Yeah, but like, why is the uncertainty in the second digit? Why is it in 1 instead of 2? Because what differs between 21 and 19 is the first digit, isn't it?
No, it's actually, where's the plus or minus? It's not plus or minus 20. It's not going 20, 40, 30. It's varying in the second digit, plus or minus 2. Okay? Now, once you get this, I'm going to show you how to pick up any tool. So I had to bring tools because we're not in the lab. And whatever the tool you have in your hand. So I brought a few around. And you can kind of, doesn't matter what the tool you have is. Kind of passes around. These all have different amounts of uncertainty on them. Better precision. Some are more precise than others. And I'm going to show you how to, based on your tool you're using, how to write a measurement based on the tool you have in your hand. So every one of these could measure, you know, 2 of them are 5 mils. Like the one you have in your hand, it's 5 mils. The one you have in your hand, 5 mils. But how you write it down is they're different in how precise they are. So I'm going to write one down different than the other based on what I have in my hand. So this is the whole goal, is I want to teach you how to do that based on the tool you have in your hand. And then that'll be kind of it. Well, then I'll show you how to do that calculations. I guess that's part. Then I'll get to the significant figure thing, and then that'll all start to make sense. Okay. Now, the measurement we use, if you're doing it mathematically, is actually standard deviation. If I take a set of 10 numbers, and I want to know what the plus or minus is, I showed you how to intuitively do it. Like it was varying in the ones place in our case, right? Or it's varying in the tens place or whatever. But if you take the standard deviation, it will have the plus or minus, and it'll show you where that digit sits. We're not going to, you don't need to know the formula for that. Because all of you have calculators that just do it for you. Do standard deviation. You enter 4 digits, tell me the standard deviation. All right. Now, here we go. Here's another scale we have. I'm going to measure 23, but look, I have tens. I have hundreds. Thousands, 10,000s. This is a very precise scale. So when I write down a digit off of here, I'm going to give it a lot more uncertainty because it's very precise as opposed to this one. Now, just to show you what that means, I don't know if I got your point made. This is 194. This is about $1,940 to buy. You pay for that precision. Okay? But here's the goal. You ready? We're going to start learning the technique. If it's an electronic phase, it's an electronic phase. So the flow meter is probably electronic phase. It may be a gauge. If so, I'll tell you how to do that here in a minute. But if it's electronic, you assume the last digit on the electronic phase is where it's uncertain. So that's easy. How many digits should I write off of here? To the hundreds place. How many off of here? Oof. Tens, hundreds, thousands, 10,000s place. That's where it's going to be uncertain. All right, so now when I write that down, I measure 5 grams. I literally write down 5, and that communicates how good the scale is. And I didn't have to do any kind of plus or minus. I measured it multiple times. Here's a standard deviation, blah, 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 blah. You don't need any of that. Write all the digits off the face. You do the same scale over here. Oh, by the way, I put a human hair on there. That's what it is. That's what that is. Let me, I think I had it floating in. By the way, this is probably not my hair that got on here. It's my wife. She has dark brown, beautiful hair, and it's glorious, except that it's kind of almost like she's teasing me that I don't have hair, because everywhere I go, I find it. I'm like, what the hell? Are you just like rubbing it in or what? Like, okay, so I have no hair. I get it, right? Anyway, so if this hit the scale, guess what? Nothing. I wouldn't see a difference. Not very precise. But that's okay, because that's written properly. Okay, here we go. Okay, same scale, put it on here. It's going to come out how many grams? 5, still, yeah, more precision. Something. This is actually a pretty good, apparently it's a good mass. It's very precise. But, Lady Dry dropped another hair on me. All right. This scale could pick it up. So that's what that's trying to tell you. It's a lot more precise. So again, does everybody have the one take home? If it's an electronic phase, write all the digits on the face. All right, there's that. And again, you might hear it put this way. I like this example. I just think it's silly because it has nothing to do with science. Because it's someone's shooting arrows at a dartboard. Here's accuracy versus precision. We don't really shoot bows and arrows in the lab. It's kind of a safety issue. So just, that's why I don't like this example. Okay, so accuracy is how close this cluster is to the bullseye, right? That's accuracy. Precision is how consistent these arrows are to each other. This person's very precise, maybe not as accurate. If that helps you see the difference. Accuracy, how close the scale is to measuring the exact known amount. Precision is how consistent the repeat is. When we communicate a scale, the digits, we're trying to show you how precise the scale is. By the way, I say mass over here. I want to remind you that weight and mass are not the same thing. Not everybody knows that, so it's just kind of a weird thing. If I'm measuring a mass, a 5-gram scale at California, it's still a 5-gram scale in Alaska. It doesn't matter, okay? But if I'm measuring with newtons and weight, like pounds, the pound will lessen as you go up in altitude because it's the effect of gravity pulling on it. So, total side note. It's for nerds. You won't even come across that anywhere. Okay, here we go. Now, analog scale. You ready? Pick up, there's a couple of them floating around. This one's an analog scale. Here's how I know it. I have it marked off, 1, 2, 3, 4, 5, and in between there's 10 more. There's a ruler. Who has the ruler? Someone? Did I hand out a ruler to somebody? Yeah. hand at it. Yeah, it is. That thing's analog. It's got 1, 2, 3, 4, 5, right? But between it is 10 marks. Yep, there's a graduated cylinder right here. Hey, if it's graduated, why is it still hanging out around the schoolhouse? That's kind of creepy. Thank you. It's a bad thank you. Okay, so anyway, there you go. Okay, so it's marked 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Or in this case, 10, 20, 30. But it has every digit. That's called an analog scale. But you guys have the gist of what I mean when I say that, right? And your flow meters, I don't know, but if they were older style, they might actually have gauges on them and they'd be analog, right? So now, what do you do here? Whoops. Make sure. What do I do here when I see 10 and 15 and I'm like, okay, well then that's 11, 12, 13, 14. Right? What do I do? How do I write this down to show how good it is? So here's the thing. So roughly where am I at? This is 17, right? That's for sure because it has lines. True? Where am I uncertain? In between. So I always write one more digit than the line. So here I'm going to write 17.4. And you're writing 17.3. You're writing 17.6. It doesn't matter because it's the same number because of our conversation earlier. It's varying in tenths. And that's precision, and it's always one more digit than the lines given on the analog scale. Follow? So let's see if we can sort this out for this one. We can do that, and then you guys can take a look, and then just pass it on over. But it measures 5 mils, and just kind of move it back so everybody can see it real quick. Okay, so I've got something that looks like this. I've got 2 mils, I've got 3 mils, and I've got every line in between. Right? So if I had a measurement hanging out right here, starting at 2, and I go, okay, 2.1, 2.2, 2.3. Sorry, I don't have enough lines, but just pretend. 2.1, 2.2, 2.3. I know that, right? There's a line for every one of them. The line beyond I don't know, so I'm going to say like this, 1 extra digit. Even if I hit it right on the dot, I still write how good the tool is. Follow? Make sense? Graduated cylinder. What are the marks on that graduated cylinder? Help me out. What do they say?
It measures 10 milliliters and 1 milliliter.
So we got 10 and
11, 12, 13, 14.
So it goes 10, 20, 30 like that, and then it has every line in between. Yeah. Right. Okay, cool. So I now go, okay, if I'm hanging out right on the line here, right, I'm going to go, okay, I know that. And this I know too, because I know 11, I know 12. These are known. I don't know the tenths, though, do I? That's the first place I don't know. That tool is less precise than this tool. That one's only good to the tenths. This one's good to the hundredths. One more, got it? One more line beyond the lines you're showing. One more line beyond the lines you're showing. Everybody okay with that? It'll take a minute, but you get used to that. Okay, that's good. That's that. So electronic digits. What do you do with electronic face?
Write everything down.
Everything that's on the face. Okay, good. Now we go one more. This is the last one. There's electronic. I write every digit given. Right, we already talked about that. By the way, just for reality in a real lab, if I make a measurement like this is a side note. So if I'm looking at the scale and I'm watching it fluctuate right here, like I worked in what's called a dry box where you stick your hands in there and you're working and everything. Inside there it's all protected. But the scale, when it got inside the dry box, it started to vary here, not out here. Just sitting there. It would be vibrating. I can only write to here. Because now all of a sudden it got less precise. That's just practical knowledge. Okay? Just a side note. All right. Here's this one, volumetric. We got a couple of those. There's one. See it? So you can take that, pass it around, look at it. Show me the mark. Do you have one? Slightly different because it's analog because it has every line in between, right? Okay. So that only has one line on it. Here's another one. Do you guys see a little line? There's one. Look at this guy. So look at this. It's a single line. You literally fill this up to a single line and you get 100 mils. So take that, pass it around, take that one, pass it around. How many mils does it measure? 5 mils. This measures 100, but it's got a single line. That's why it's like, I mean, it's really crappy or is it good? By the way, they're worth, as you're cleaning around, it's worth a lot of money, but very expensive. Very expensive. No pressure. Right? So now what do I do with that? What do I do when it's a single line? Well, look on side, tell me the 5. Do you see a little plus or minus in there? You see a little thing in there that goes plus or minus something.
Yeah,
0.0 what?
30.
Which is really kind of a weird way to write it. But anyway, what's that one say? Does it have a plus or minus? That's, by the way, it's 5 mils. 0.08. And that's how many mils? 100 mils, right? So what it means is I'm good to 5 mils, but it's plus or minus, so I just write like this. This is where I'm uncertain. So I'll write it as this. That's how good that tool is. This one's pretty good. I can measure 100 mils all the way out to here. I'm going to just write it down like this. Oh. So when you have a single line, you have to go find the plus or minus. And if it doesn't have a plus or minus, you got robbed. You shouldn't have paid extra for it because you got to have the plus or minus. The way it works is, do you guys remember I kind of introduced that really density of water is pretty set? Remember that? You remember how many grams are in the middle of water? 1. So what happens is I will literally measure 100 grams of water on here, right? So what I'll do is, the way these were standardized is they take that 100 mil thing, they literally fill it right to the mark, and they measure the mass. And so let's say that they're measuring the first time it's 100. The second time it's 99.99. The third time it's, you can imagine, on and on and on. Before long they go, guess what? It's varying in the, yep. And they do the standard deviation, and that's where this exact number comes from. And we don't have to get bogged down in that. All we need to know is it's uncertain to the hundredths place. Make sense? That's important. So now, when I use a syringe, right, use a syringe, and I'm saying, oh, I am actually administering, apparently here's the lines on it, 1 microliter, 2 microliters, and then I look and see 1, 2, 3, 4, 5, 1, 2, 3, 4, and they're like that. Follow? And I dispense right to the line. Hey, you're supposed to do 2 microliters, right? So you go, okay, that's 2 microliters, but I want to convey how good this tool is. And they go, okay, anybody want to help me? 0, 0. Because I definitely know the tenths, so I'm going to go 1 more, and that's how good it is. And then somebody's kind of slopping around, and they find one that looks like this, with no lines in between, and they go, oh, I'm going to dispense 2 mils. What did they really dispense? 1. Because I don't know, that's a microliter, by the way, sorry. Because I don't know, the first place I'm uncertain is in the tenths. Now, what does that mean? It means that if you're sensitive to medicines in that degree, that's not a good enough tool.
Even though you're uncertain on that last one.
Oh, like that, here I would go 2.0 microliters, is that what you mean?
Yeah.
Yes, that's what I would do.
Okay.
I don't know why I did that.
But it's essentially.
But it is actually the same thing. You writing 2.1, me writing 2.0 means the same. It basically conveys that I have measured around 2, but I have a plus or minus in the tenths. And if I cared, like some medicines were careful down to that tenths matters, this wouldn't be the tool. I'd have to drop down to the better tool. That's accurate. And it's the only place I'm uncertain is in hundreds. Making sense? Okay, cool. That's the whole beginnings of significant figures, and that's what people don't always get across. Now, once you know that piece, then you can do calculations with it, and I got to maintain that precision. Follow? If I start with a tool in the lab and it has a volume, and then I'm about to do density where it's mass divided by volume, I've got to still convey the precision that was in that original measurement. I can't come up with an answer that's all of a sudden, the original measurement was precise to the microliter. But now I do a calculation and I make it 0.0001 microliter squared or something. It's like, how did I all of a sudden become so precise? Right? You follow? So that's where we go next. But first, I'm going to do this real quick. Kind of have 3 scenarios. This would be what the questions would look like, so you know what it looks like. Is everybody okay with my pictures? That is an electronic scale. What would you call this? It's analog, right? And then this one I'm trying to say, hey, it's a 250 ml flask, but it's got this plus or minus 0.01 marked on the glass. So how do I write this down? If I filled it right to the 250 mark, how should I write that down? So take a minute, make sure you follow. Everybody put down these 3 answers. Then I'm going to just randomly ask somebody to help me out. You ready? Talk to your partners, your neighbors, so you see that you agree. Stop, partners. What did you get? What did I get? Do we agree? Okay. By the way, if you're back there answering this question, you might have to come walk over here real quick. The way you view this question is going to be different. You guys over in this corner, you're going to have a problem seeing this. You might want to come look at it and see where that purple is on that line. So if you guys need to move, go ahead. So 3.6 and 3.7. I mean, depending, I have to look at it. So I think it's sitting kind of on this side of the line. So then what do you have? 6 is known. So 3.6. Oh, yeah, that part of it. You need one more digit to be on the one the other. All right. Are we ready? Somewhere in the back corner, you two gentlemen, can you help me out with what I'm going to write off of here? Is that all the digits exactly as it's given? Agreed? Okay, good. Sounds good. Check. Guys ready? So we'll go over, and I know we talked about this, so I asked you 3 back there. How are you going to write this down?
0.610 or 1.
Yeah, so So she says 0, you say 1, does it matter? Yeah, we're both right. That's good. 3.6, and then one more digit beyond what I'm given. Good. You guys ready for this? How do you record this?
250.0.
250.0. Good, good, good. Is it enough? Okay, cool. You're off and rolling. So now I'm going to have you do something real quick. I'm going to give you a unit that you should probably know anyway, so we'll just make use of that to do a calculation. Okay, got a minute? See if we can pull this off. All right. So here's your first formula. This is not a conversion, it's a formula. It's saying the concept in science of density is how much mass per unit volume. Okay, and that actually has some relevance for you. Okay, so I got a couple. Here we go. Of these, which is more dense? This or this? Shot put, right? There's a lot more mass per unit volume. Right? So density has something to do with something. Now, heads up, everybody should know in science that the density of water in standard conditions versus standard temperature pressure is 1. We use that, like we use it to calibrate tools quite often. Like I'm going to make sure my masses or my volume's working. I'll put 100 mils in there. It should measure out 100.00 grams. Make sense? Sometimes this is called specific gravity, just in case you hear that thrown around. It's a weird word. Specific gravity. I can't even tell you what that means. But just so you know, it means density. Same thing. If you go to get your radiator checked, they might say, we're going to check the specific gravity of the radiator. What do you think? If you're trying to figure out the density, you can figure out the density if you have enough antifreeze in there or not. One thing is helpful, it gives the identity of the pure substance. So if I, decide I'm going to get some gold plating, right? So I got some bling when I'm in here at Dr. T really pops, right? So if I want to know that it's pure gold, right? Or my wife's like, nice ring, but I'm not quite sure about you. I'm going to check out if it's really pure gold, right? So basically that gold on waves. They look like a river. Isn't that cool? So my wife's family. This is my family, and this is God in the middle. And we got to get, isn't that cool? Sorry, I know. I shouldn't have started in on this. But anyway, if I wanted to know whether this is pure or not, I could literally figure out its density. Because the density of gold is, right, you can't, like if I had bought her a little aluminum foil plated in gold, the density would be off. It'd be wrong. So that actually is relevant a little bit in your business. They do density adjustments sometimes to figure out the amalgams you write. You guys don't use that so much. That's like a thing in the past. But you might have metals for sure, right? Titanium or whatever. You might use some sort of fastening materials. So that's that. I also let you know that really density is the key to floating. This is kind of the physics concept. Okay, Archimedes' principle. Less dense stuff floats in more dense fluids. Fluid can be anything that moves, whether it's liquid or gas. So if I am less dense than gas, I would start floating. That would be cool. Right? That would be cool. The same thing like a boat floats in water because mass per volume, it's less dense than water, which is 1. So that's cool. All right. So we're going to measure a cal. It's a very small cal. It's a little bit under an inch wide, and it's about an inch long. This is a little bitty cal. It's like if you want just a little drink of milk. That's all. Right? So we're going to just roughly figure out the density of this cal. You ready? So I'm going to do it like a box, and I'm sorry. No offense to the cal, but we're going to measure it like a box. It's just simpler. We're going to say it's about this long. Ooh. Anybody want to give me a number for that?
3.5.
3.4.
You know what's kind of cool is 3.50 and 3.40. If this is important that I'm looking straight on, so I'm seeing it fall about like that. What would you say then?
3.43.
Okay, and somebody, 40 and But for some reason, I'm really messed up. Sorry. 3.40, or somebody back there arguing going 3.43. Same number. It's okay, right? It's okay. Good. Now, how tall is it? 2.50 centimeters. How wide? 1.23 centimeters, right? So now what we're going to do is figure out the volume of that cow, which is width times height times length. So now here's the catch. I'm going to get an answer, but I don't want to give up my precision. Like, I don't want to make it more precise and less precise. But let's just do the calculation first. By the way, I've got to be consistent with my slide, see what I thought. I said 346, geez, whatever. So if you want to just use that number so you can, the calculations agree. Multiply those three together, and what do you get for the volume of this cow? Give me all the digits you're getting. What do you get? 4? I'm hearing a lot of digits, but help me out.
10.54.
Is that good?
10.6395 with 3.46.
Yeah. So using that, is that okay? Is that okay? Just multiply the three together. Does that agree? Here's the problem. This number just got a lot more precise than these numbers started. Right? This tool is only so good. So how do I communicate this and not all of a sudden pick up new precision? So this is where significant figures came from. It's basically a way that we can track precision through calculations and not gain or lose precision. So the way you do it is you have to count the number of significant figures. And the way you count, and we're going to learn these rules real quick, but it's basically if they're integers, they count as significant figures. But now you know where these numbers came from. They're not just any numbers, they're based on what kind of tool it was. And now I go, oh, there's actually 3 significant figures. There's 3 here, there's 3 here, and there were 3 in there. So the answer can only maintain 3. So now I just got to cut it to 3 significant figures and say 10.6. And the units? Cubic centimeters. Which if I convert it to mils, be the same. Perfect. That's how it all ties together. You with me? Okay, we do that. Now we put it on the scale. Oh yeah, got a way in there. I'm going to move it over onto the scale. Sorry. All right, here we go. Whoa, nice skill. My gosh, that's a good skill. All right, wow. So mass divided by volume, if I do it all together, I get a density that way too many digits. And although it's a very good skill, does it matter? Not really, because I'm still stuck with 3 significant figures. 0.231 grams per cubic centimeter. Follow what I did? Okay. Now, based on that, is it more dense or less dense than water? Less dense. That's kind of cool. So what that means is this thing could actually float. So I got all right. So we're out of time, but when we get back together, I'm going to show you how to count digits and track them through calculations. And I hope that I can wrap that up and start doing things when we're together next. All right?